Data centers play a critical role in the digital infrastructure that powers our connected world. However, they come with a significant challenge: keeping the facility cool. The high-performance servers and equipment generates large amounts of heat as a byproduct of computation, which demands constant cooling to ensure their reliability and performance. But what if there was a more efficient and less electricity-intensive way of keeping data centers cool? Let's take a look at a data center powered by electric chillers. In this video, I'll show you how adding a combined heat and power, or CHP generator, plus an absorption chiller enables you to improve the financial performance of the data center. Let's break down how the data center is kept cool. First, we need to model our cooling demand, which is how much cooling power is required by our data center on a daily basis. In Xendee, users can either upload, build, or import a cooling profile. If you already have a time series data file for your data center's demand, you can directly upload it. As an example, I'm using 8760 data here from the previous year. But if that was unavailable, we could import a similar facility schedule or build our own using the load builder. Now the cooling profile is defined. Note that I have also added the electricity profile for the data center. This is the electricity used by the data center for its operations and does not include the cooling. Let's add the existing chiller to show how the cooling demand is currently being met. This will be our baseline scenario. In Xendee, we set the electric chiller to existing and enter the current capacity. The electric chiller in the current base case is powered by electricity purchased from the utility. With this demand, it currently costs $25 million in utility charges. This includes both the electricity to serve the regular electric demand of the building and the demand of the electric chiller. As we can see, this setup relies heavily on external electricity sources, making the data center vulnerable to utility price volatility and potential grid failures. The final optimal solution will consist of a CHP generator and absorption chiller, as we'll see later on. But first, I will introduce generators and assess its benefits. How can we improve the cost efficiency of the data center? Let's first take a look at how gas generators in general can help reduce utility costs. Let's add a generic gas generator to the model. Since we don't know how much generator capacity is best to supplement the electricity demand, set it to consider. We also set a maximum number of units to limit the amount of capital expenses. We set the optimization objective as reduced cost, and a quick optimization tells us the optimal generator investment as well as annual savings incurred as a result of this investment. The dispatch shows that the generator is utilized throughout the day to supplement the electricity demand. This reduces electricity purchases from the utility, which reduces both electricity charges and demand charges. So now that we've seen how adding a regular gas generator can help the electric efficiency of the data center, let's now take the next step and change the generator to a CHP generator, as well as add an absorption chiller. So how is a CHP different from a regular gas generator? A CHP system generates electricity while capturing the waste heat produced during this process. That waste heat, rather than going to waste, is channeled to an absorption chiller, which uses it to provide cooling for the data center. The beauty of this approach is that it reduces the need for grid electricity, providing both power and cooling in one integrated solution. Let's model the CHP and absorption chiller. We can utilize the same gas generator setup as before, since CHPs are still a type of gas generator. To designate this generator as a combined heat and power system, I turned on the CHP toggle. Now we need to add the absorption chiller to the model to complement the CHP. Similar to the CHP, set the absorption chiller to consider to let Xendee solve the optimal capacity. With the new round of technologies, we're ready to optimize again. Again, the optimization tells us the optimal sizes for the CHP and the absorption chiller. Let's take a look at how this integrated system works. In the dispatch for a peak July day, the CHP generator supplements the electricity demand. The heat dumped by the CHP is then used by the absorption chiller to supplement the cooling demand. This reduces electrical demand from the grid. As a result, we can clearly see savings in both electricity and demand charges compared to the data center's current scenario. However, we can also compare this setup with a generator-only setup to see how much savings is due to improving the cooling efficiency. Remember, we previously ran an optimization with a gas generator-only case. We can use that optimization as a baseline for our new model. This will compare the system using a CHP plus absorption chiller to a system using only a gas generator. As you can see, this new optimization calculated the savings using the gas generator only scenario as the baseline. This allows us to realize how much of savings come from utilizing a CHP generator instead of a regular gas generator, as well as complementing the CHP with an absorption chiller. So there we have it. By modeling the cooling demand of the data center in Xendee, we see that adding a CHP generator and an absorption chiller can help reduce utility charges. What topic in designing microgrids do you want to see next?